So in our last couple of sections, we've introduced ourselves to the idea of confidence intervals and hypothesis tests. In particular, we were looking at one population and using the sample mean to try to estimate the population mean. And in this section, we're going to talk about, it's called inference and practice. So the real world things you have to consider when you do that, aside from just the routines that we go through and the formulas we use, what do we have to consider in the real world? But first of all, I can summarize what we've talked about. So if we have a sample from a single population and we're trying to approximate that single mean, then we can do a confidence interval, which is your sample mean x bar plus or minus your margin of error, which is z star times sigma over square root of n, where sigma over square root of n we know is the standard deviation of the sample mean, and z star is that value on the standard normal distribution that captures c% of the population in between z star and negative z star. Call it the critical value. So that's our confidence interval, which is an interval that if we have a c% confidence level, then that's how confident we are that the actual parameter is in there. And then in the last section, we looked at hypothesis tests. In particular, we looked at the z-test, where our null hypothesis was that mu was equal to some value, say mu sub 0, and then we had our alternative that could be a less than, greater than, or a not equal to. And in that case, you're computing a test statistic using x bar and then doing what's the probability that that would occur if the null hypothesis were true. So you're using your sample data to try to find evidence against the null hypothesis or not. You either conclude that you reject the null hypothesis or you fail to reject the null hypothesis. So those are the Z procedures that both involve, again, one sample statistic. You're looking at the population mean using the sample mean, and we're using the standard normal distribution to do it. And in both cases, we assumed that we knew sigma, which is pretty unrealistic, and we'll have to use the T procedures more often after we've mastered the Z procedures in the real world. Some things to think about, though, and you can read through this yourself, but whenever you read a study and people are trying to convince you of something in a study, you need to look at where did the data come from? Did they collect the data wisely? As we talked about in chapters 8 and 9, is there randomization going on, or is there some sort of bias? Was there a lot of non-response or dropout that can bias, say, a study? So again, there's no cure for fundamental flaws like voluntary response or convenience samples and those types of things. If you want really convincing data, it needs to be based off of random sampling. And the shape of the distribution, sometimes in here we start working these problems and take this for granted, but if you have a population that has extreme outliers or strong skew, we know that the mean, including the sample mean, is not resistant to those things. So we have to look out for those and be aware of that in real life. Some other cautions. Sample size. So sample size, there's good and bad of large sample size, I want to point out. You want a large enough sample size so that you can detect statistically significant differences. And we'll talk about power later, which is a probability that you're able to detect certain statistically significant differences. A lot of S's and T's in that statement. But if your sample size is really large, any difference is going to wind up being statistically significant if your sample size is large enough. So we like to mention that a statistical difference does not mean you necessarily have a practical significance. For instance, if you take the SAT, which is measured in the hundreds, and you find you have a large enough sample size, you might find that a 1-point difference in the averages is statistically significant, but that's not practically significant. The difference of 1 point on the SAT is nothing, you know. Or if you're looking at like average salaries or something and you find a $1 difference, but your sample size is so large, that might be statistically significant, but it wouldn't be practically significant. So there's this balance between having a sample size that's too small and too large. Or if you do get a statistical significance, you need to actually look at the data and see, is it a practical significance? And then later in the class, when we talk about ANOVA and chi-square, those are both tests of several things going on at a time, of multiple comparisons. You have to be careful of running individual statistical tests over and over, because think about it. If you have a p-value and you have an alpha level of 5%, and so you're saying something shouldn't occur more than 5% of the time by chance. Well, if you do it 100 times, then you expect it to occur 5 times. So the more often you do something, the more likely it is that by random chance you'll get a result in a certain way. So doing a test over and over kind of deflates the power of your significance. It deflates your significance test. So beware of multiple analysis. There's procedures that have been developed to take care of those things. And then the next thing we're going to talk about are the possible errors that you could make.